Hello everyone, I'm Lorenzo Leandro from the Quantum Machines team, and I would like to talk about 2-qubit randomized benchmarking, and specifically I would like to show you a new QUA package to streamline RB in your everyday life in the lab. So first, a very brief introduction of randomized benchmarking for 2 qubits. So obviously we need to be able to prepare the qubits in the zero state, and we need to be able to generate a random sequence of Cliffords and also to play the sequence. So this is not necessarily very easy to do. Specifically, we need to be able to generate a random sequence. This is usually done on the PC before the sequence even starts. And then we upload the sequence on AWG memories, for example. And then we also need to be able to invert the sequence and play the inverted sequence. The idea behind this is that once we apply a Clifford and then we apply the inverted Clifford, we get the identity back. So after having prepared the qubit in the zero state, when we in the end measure, we should be measuring zero state again. If we measure anything different than zero, then we are evidencing an error in the Clifford sequence that we do. So if we, for example, apply a number of Cliffords and then the inverted same number of Cliffords, we get out a 1, then we are evidencing the error that has accumulated over many Cliffords. So the number of Cliffords in the sequence is what we will call depth of the randomized benchmarking. And this obviously allows us to evidence the average Clifford error. So if we take an example from literature, we see that we can apply many Cliffords, and the more Cliffords we apply, obviously the higher the probability of obtaining something that is different from zero. So the probability of an error increases after saturating at 0.5. So this is the probability of obtaining a 1 measurement. So in order to obtain such a graph, we obviously need to implement this in a cycle. So we need each Clifford sequence, or each depth of Cliffords has to be repeated many times in order to get an averaging. But also the whole sequence needs to be repeated many times in order for each of these x-axis points to have multiple gray spots in order for us to make a proper fit. Once we do this, obviously the Cliffords will look differently. These are randomly generated sequence, so every time we repeat with a different actual sequence of gates. So this is how it's usually done, and it's also usually extremely slow of a sequence because of all the mathematics computation that we have to perform to generate and play these random sequences, to invert them. But also it's very slow due to the fact that we upload into memory a very high number of waveforms that need to change and need to so we lose a lot of time into loading of sequences and the communication between the PC and the hardware that is actually playing the pulses. So this is obviously solved from the OPX point of view. We don't have this problem because QUA takes care of the running of all the mathematics and all the generation and inversion of the random sequences right down on the FPGA. So there is no more loading sequences. There is no more compilation time, and all the loops run on the FPGA. In addition to normal 2-qubit randomized benchmarking, there is also a possibility to do an interleaved circuit where we can evidence the error coming from a specific gate. So this is the red curve showing here, where we have the blue curve showing here, where we evidence the authors evidenced a C0 error. To read more about the 2-qubit randomized benchmarking sequence and how it works and how the gates are also defined, I would suggest you to look at this Martini's paper from 2014. It's a reference that we use very often for RB. So let's look at these building blocks that we discussed that you need to be able to provide in order for the sequence to work. So the first is obviously to be able to perform single qubit and 2-qubit gates. The Cliffords are composed by single and 2-qubit gates, and this is something that you can quickly understand going through the reference from the 2014 Martini's paper. So single qubit gates, I'm just going to show an example of what we use today. Today at QM, we use the phased XZ gate. This is how it looks like in QUA. So to note, basically this is a generic gate that allows you to perform any single qubit gate depending on the parameters that you provide. And also we use the baking tool. So today this QUA package only works with the baking tool. For those of you who are familiar with it, this is a tool that allows to use QUA for pulses shorter than 16 nanoseconds, while usually the lower limit is 16 nanoseconds. It doesn't change a lot from the usual QUA syntax, so it should be pretty simple. Basically, adding baker dot at the beginning of each function. It should be roughly the same as writing in QUA. 2-qubit, same goes. We usually use a CZ gate. So you can also download the code from our GitHub and look at how we define the gates. You can obviously implement whatever 2-qubit gate is available to you. If you have at least a C-Not-like, a swap-like, and an I-swap-like gates, then you can perform any 2-qubit gate with the addition of single qubit gates. This is also very well explained in the Martini's paper, and you can very easily add new gates whenever they're available in your lab. And the code runs the prioritization of gates behind the scenes, so you will always be using the most efficient gate available to you. Then obviously you need to be able to prepare the qubit and to measure the qubits. For the preparation, the easiest way is to weight 10 times D1. This is very common, but the OPX, as all of you know, also allows you to do a very fast active reset, around 200 nanosecond latency. This speeds up the sequence substantially, obviously. And then the measurement, here we just show an example of the code we use today. It's just a full demodulation to get the I values for qubit 0 and qubit 1. Obviously, to make 2-qubit randomized benchmarking, you also need to be able to perform calculations. You need to randomize the sequence and to invert the sequence. This is usually done in Python or in a lab PC. We do it on the FPGA to get everything running as fast as it can. So, and this happens behind the scenes, so you won't see any of this calculation happening. Just to show you how the code will look like, so the first 4 macros are the building blocks that you have to provide. You have to show the code, what single qubit and 2-qubit gates you have available, and you have to define macros for preparation and measurement. And then this is how the RB actually runs. So the first line to run RB is the configuration of the experiment. You have to provide the macros that run single qubit gates. You have to provide a list of 2-qubit gates that are available, and then provide the macros for preparation and measurement. And then the second line is our rb.run, which actually runs the sequence. Here you have to provide the depth that you want to be evaluated during the protocol, and then the number of repeats and the number of averages. So this is the 2 loops that we discussed at the beginning. One gives many one moves from having a single shot 0 or 1 measurement to have a probability of 1 or probability of 0, and the other allows for many of these measurements to be obtained for each depth in order to have a better fitting protocol. And then obviously you can very easily plot the results of the fidelity. Here today I'm just going to show you how, what is the output if we look at the scope to the I values for qubit 1 and qubit 2, and then the flux line and the measurement line. You see that the sequence gets randomized, and so you see every time it updates, it's a different sequence. Here, obviously, I'm slowing down the process substantially in order for the animation to be readable in some way. But this is just to show you how the randomization looks like on the output of the OPX. So the code is available to you today. If you have any questions, we are here for... The code is available to you today. Contact the local customer success person or write us on Discord to help to use the QUA package. Also, we are working on implementing new functions in this package. For example, we're going to release a version with the ability to do interleaved gates. So this will allow to measure the errors of individual gates rather than just the Clifford or the average Clifford error. So this will come in the future, and more functionalities will come as well. But as of today, we have sequences that run maybe in a minute or two, rather than going on for hours loading and calculating. So the OPX takes care not only of all the loops, but also it performs the calculation of the next sequence while you are performing the current protocol, the current run of the RB. So it optimizes this substantially, and we are working to optimize this even further to get this measurement really done in an efficient and timely manner. Thanks for the attention. Contact us if you want to hear more or implement this in your lab.